Hello everybody and welcome to Science World's special live presentation today. My name is Cindy. I'm a science facilitator here at Science World. I would just like to start off by acknowledging that we are on the traditional and unceded territory of the Musqueam, Squamish, and Tsleil-Waututh peoples. And I would like to encourage you to take a moment to learn a little more about the history of the land you're on and its unique stories. Now, I am a science facilitator here at Science World, and what we love is to do science. So we are very, very excited to be able to participate in the Family Day activities with the City of New Westminster. I'm excited to be here, and I hope you have a great Family Day, and I hope after this that you're checking out some of the other awesome activities that the City of New Westminster has available. Now, it's been a long time since I've been able to do science presentations in front of a live audience, so I am excited to do some presentations for you today. Some of these demonstrations are my favorite demonstrations that I used to do for people who came into Science World and also for our online audiences. So I hope you find them as fun as I do. The first thing that I wanted to talk about in terms of our science demonstrations is air. Now, air is very, very important, and air used to be still is one of my favorite things to talk about, because you can talk about so many things when you talk about air. And what I actually like is to do a quick demonstration with air that uses this. Some of you might have seen this before, and this is what I like to call some super special science paper. It is called science paper. It is called nothing else but science paper, okay? So, I'm going to use this super special science paper. I'm going to show you something called the Bernoulli Principle. Now, the Bernoulli Principle is a very, very commonly seen principle around the world in nature, and it basically says that fast-moving air creates an area of low pressure. And what that might mean is that if I were to blow fast-moving air across maybe the top of this science paper, we might see something really interesting happen, because when there's an area of low pressure created, a lot of times air from around that area of low pressure wants to go in and fill that gap. So, before I do this demonstration, I want you to turn to the people around you, even if it's just your cat, and I want you to make a prediction about what might happen if I were to blow some fast-moving air across the top of this science paper. So, I'm going to make sure I'm turned away from my technician, Brian, and that we are about 2 meters apart, and I'm going to very, very carefully blow some fast-moving air over the top of our science paper. 1, 2, 3. Whew! You might have noticed that something really interesting happened, because when I blew that air over our paper, you saw the rest of that paper move up. And that's the air underneath, pushing the paper up when it wants to take the place of all that air that I blew over the top of the science paper. But you know what? This is only 2 pieces of paper, so I think we can do it on a bigger scale, which is why I have my lovely technician, Brian, with us today. And you might be able to see his hand there. And what we're going to do is we are going to try and get this whole roll of science paper lifted with some fast-moving air, and we're going to do that by using a leaf blower. Now, leaf blowers are very useful tools. I'm going to hand that back to Brian. Some very useful tools for maybe, blowing leaves in your neighbor's lawn in the fall. But what we're going to do is we're going to use it for some science, okay? Are you ready, Brian? All right, and I'm going to get some safety goggles on for this demonstration, because I don't know where that toilet paper, science paper, is going to hit. Okay, now I'm ready. Are you ready? And in 3, 2, 1. Woo! We got a whole roll of science paper lifted up and, maybe blown into my face a little, but that's okay. I'll forgive Brian for that. I know that he didn't mean it and that was an accident, but that's pretty cool. And that's the Bernoulli Principle in action. But there's a lot more about air that maybe we haven't thought about. And what I wanted to talk about was something called air pressure, because we know that air is all around us. It is surrounding us every moment of every day. And what it is doing is air is always pushing. It's always pushing. And, I have this bottle right here, and I want you to, using what I just said, I want you to make a prediction as to what's inside this bottle. Here, I'll even turn this bottle upside down. But there is something inside this bottle. You might not be able to see it, but inside this bottle is air. Just like there's air all around us. And what I'm going to try and do is I'm going to try and take this little piece of paper right here, little ball of paper. I'm going to try and blow it into our bottle. Easy peasy, right? This is, they told me to do this demonstration. I don't even know why, because I'm just blowing a piece of paper in a bottle. But let's see what happens. Okay. So I got our piece of paper lined up and ready to go. Got our bottle. Once again, I'm turning away. And 3, 2, 1. What? What in the world just happened there? Seems like maybe the air in our bottle actually pushed that piece of paper out right back at me. That was pretty rude of that piece of paper and hit me in the nose. But the cool thing is, air is all around us. It's pushing all around us. And what we can do is we can actually take that air and we can manipulate how much air is in a certain container. And that's exactly what we're going to do with our vacuum chamber here. So if I put this lid on this vacuum chamber, we know, as we just discussed, that there's something inside this vacuum chamber already, and that something is air. What we also have is we have my friend. His name is Steve. He's a balloon, and he is a very, very nice balloon. Steve is one of my best friends, and Steve is also full of air. So when we think about balloons, we know that they have lots of air in them, and the more air, the bigger they are. But we also know that the thing balloons are made of, the rubber, is stretchy. And we have to keep that in mind, because we're going to put Steve in our vacuum chamber, and we know that our air is pushing. The air is always pushing. It's pushing in every single direction all around us. The air inside Steve is pushing too. So when I turn on this vacuum chamber, which is going to remove a lot of the air from around Steve, I want you to make a prediction as to what you might think might happen to Steve. Is Steve going to get bigger? Is Steve going to get smaller? Is Steve going to pop? I sure hope Steve doesn't pop. Steve's a really good friend of mine, and I really hope he stays intact. All right, let's test it out in 3, 2, 1. Might be nice to plug in our vacuum chamber before we do anything with it. We will give that another shot. We're going to test out our vacuum chamber in 3, 2, 1. Whoa! Whoa! Look at Steve go! Steve is growing so big, growing so strong. He was just a tiny little balloon before, and now, look, Steve has grown massively. All right, let's see how big we can get Steve, and I like the look of that. So when Steve just used to be a tiny little balloon. Now Steve looks like a full-grown balloon. Steve has gotten real big, and all that air inside him was able to push outwards on his rubber exterior, and now he's gotten nice and big. So I'm just going to take Steve out of the vacuum chamber here. Oh! Oh! Oh, wait, I actually forgot. Since there's not that much air left in our vacuum chamber, I have to remember that the air around us is pushing down on the vacuum chamber so hard. It's kind of hard for me to open up. Wonder, maybe I can let the air back in, see what happens then. Whoa! Oh, well, looks like Steve has gone back to his original state. Thank you, Steve, so much for participating in that demonstration. And I just wanted to show you one last demonstration with our vacuum chamber, and we are going to use Larry. Now, Larry is my other friend, and you might notice, but Larry is a marshmallow. Larry is my favorite marshmallow in the world because Larry has a very special face drawn on him, and also I love marshmallows. Marshmallows are delicious. I like to say that marshmallows are made of 3 ingredients. They are made of sugar, they are made of air, and they are made of magical, delicious fluffiness. So, what I'm going to do is I'm going to put Larry in our vacuum chamber. I'm going to see if the air bubbles, the air pockets inside Larry, the marshmallow, are going to do anything particularly interesting. Okay, now that we saw what happened with Steve, maybe we can make a prediction as to what happens to Larry in 3, 2, 1. Whoa! Check it out! Oh my goodness! Larry seems to have grown into a full-grown marshmallow as well. That's awesome. I'm going to take Larry out, and we're going to have a big celebration that Larry got so nice and big. All right. Whoa! Larry, what happened to you? He's all small and shriveled now. That's so sad. But either way, so vacuum chambers are very, very interesting tools, very interesting pieces of equipment to see how things might react in lower air pressure, or I don't think that they can create higher air pressure, but it's cool to see what might happen when the air around something gets taken away and how that thing reacts. So that was our vacuum chamber. Very, very cool demonstration. And we are going to move on to talking about sound. I really like sound, and I love learning about sound. And one of the really cool things that I found was that you can learn its sound at home. So what I have here is my straw, is a straw. And what I've done is I've actually cut the top piece into kind of a little triangle with the tip cut off like that. I've chewed it so it's flat. And what I'm going to see is if I can make a sound with this straw. So let's give that a try. And well, that's a pretty fun sound that I made. But I wonder if I can actually make different sounds using one straw. And the really cool thing about sound is you can experiment with it in all sorts of ways. So what I'm going to experiment with is cutting the straw oboe, which is what I like to call this thing, a little shorter every time I blow, and seeing if that makes a difference. All right, let's try that out in 3. Actually, let's make a prediction about if that makes a difference, and we can test that prediction in 3, 2, 1. That's some pretty cool stuff to do with sound, and feel free to try this one at home, but make sure you're being safe with any scissors that you might use. What I actually did was a long time ago, not that long ago, I actually made a really fun video about sound at home. And this is a really cool demonstration that, or a really cool activity that you can do at home, is creating your own cup telephone. So I think we have that video loaded up.
Hey folks, it's Brian and Cindy from Science World, and we've got a really cool demonstration that you can try at home with just a few simple items. We've got 2 cups, we've got a bunch of string, you'll see why in a moment, and we've got 2 paper clips. If you poke a hole in the bottom of your cup and then fish your line through and just tie it off with a paper clip, that'll keep it in place, and it allows you to throw it down to someone that can help you with the demonstration. So I'm going to throw a cup down to Cindy, I'm going to hold on to the other one, and we're going to demonstrate how sound is vibrations, but those vibrations don't always have to travel through the air. Now they will travel through the air a little bit in this demonstration, but there's also going to be some vibrations that happen in Cindy's cup, and those vibrations are going to travel through the string, and they are actually going to end up in my cup over here. Now I can obviously put my cup up against my ear, but I've got a microphone here so then you can hear the results at home. I'm going to put the microphone beside the cup so it's kind of as if Cindy was just talking into a cup and I didn't have anything special going on, so let's try that. And then I'm going to put the microphone inside of here, inside our cup telephone.
Can you hear me?
Woo!
If you guys are going to try this at home, feel free to share it on social media with the hashtag #ShowUsYourScience so we can see all the cool things that you're doing at home. Have a great day.
That was a really fun activity, and an activity that you can do at home with all sorts of different things. Any cups that you have lying around, any strings, and making some observations about how the different cups or different strings might affect the sounds that you get. But now it's time to move on to some of my favorite topics in science. And those topics are the topics of moving things. I love to learn about moving things because there's so much to know. And one of the really fun demonstrations that I like to do is a demonstration with something like this. Now this is called a Greek's waiter's tray, and what it does is it holds a cup of water, nice and simple. Greek waiter's tray, holding a cup of water. But what we can see is that if I take my waiter's tray and let's say I swing it around like so, we can see that our cup of water is doing a really good job staying where it is. And that's because of something called inertia. And what inertia means is that things that are at rest, for example, our cup of water, typically want to stay at rest until a strong force is acting on them. And now we can see that our water has some inertia that's keeping it from maybe falling off the Greek waiter's tray. But, ooh, and we saw that gravity there almost took the cup of water, almost overcame the inertia, took the cup of water down. But that's going to lead nicely into what I want to do with our Greek waiter's tray is I want to see if I can swing it all the way around with our cup of water staying on it. All right, seems like quite an interesting feat, and what we're going to see is we're going to see if I can do it. And I want everyone at home to make a prediction, see if this cup of water is going to stay on the tray or if it's going to go flying everywhere. All right, make your predictions at home, and I'm going to try this out in 3, 2, 1. Woo! Whoa! Look at that! Greek waiter's tray, cup of water, still perfectly intact. That is pretty awesome. So you might have just seen us do this Greek waiter's tray over there. And a really fun thing that my friend Stefano did earlier was he actually put his phone on the Greek waiter's tray and recorded what it looked like from his phone's perspective. So I want you to make a really quick prediction in your head as to what might happen with Stefano's phone when he put it on the Greek waiter's tray and spun it around. What do you think might have happened? And we can take a look. Whoa, okay, there's Stefano. Oh, hi, Stefano. Waving at his phone. Maybe waving at me. All right, he's raising that thing up. And go! Oh, my goodness. Whoa. Is Stefano spinning or is our phone spinning? Whoa, that was pretty cool, Stefano. And nice job. It looks like your phone was safe in the Greek waiter's tray. Chemistry is all around us, which maybe sometimes we don't do chemistry where we are working with these flasks or working with graduated cylinders, but chemistry truly is all around us. And what we want to make note of is that the chemistry around us and the chemicals around us and the chemicals that we use always need to be used in a controlled setting. So even if you have chemicals in your household that you think you might be able to do experiments with, we want to make sure that we have a trusted adult with us and also the proper safety equipment to keep us safe when we are doing chemistry. And speaking of which, I do need to go get my safety goggles to make sure that I am being safe when I am doing chemistry. Better. So, what we are going to be talking about, the first thing we're going to be talking about with our chemistry is we are going to be talking about acids and bases. Now, those words might be familiar to some, might be a little less familiar to others, but what acids and bases are just very broad groups that a lot of scientists like to categorize chemicals. So acids are things like lemon juice or vinegar, where things might taste a little sour, or maybe like it might burn a little if you let it touch your skin, but we have to make sure we're not tasting a lot of chemicals, because we don't want to ever put anything in our mouth that we don't know what it is. But acids are one very broad group of chemicals, and the other one is bases. Now, bases are a little different from acids. They might feel a little slippery, they might taste bitter, and they have a property where they're caustic. So if they touch your skin, they can cause things called chemical burns. And that's why we make sure that we are always wearing our safety equipment when we are working with both acids and bases, because both can harm our skin. But what we are going to do is we are going to use something called an indicator. And an indicator is something that actually will tell us if something's an acid or a base. And these are common chemicals too. And there are some common indicators that are in your household. So things like turmeric is an indicator. Things like red cabbage juice is also an indicator, and might change based on whether they are exposed to an acid or a base. And that's something really, really cool to experiment with at home. But what I'm using is an indicator called Bromothymol Blue. And Bromothymol Blue is a cool indicator because when it's in water, I just mixed it with a little bit of water, you can see that it's this really, really interesting green-blue color. But it might change if I do something very simple. I'm just going to blow some bubbles into our flask right here. So let's give that a try and go. All right, let's take a look at what our liquid looks like now. We see that it's turned into this really, really cool, really light yellow color. And that's because when I was blowing bubbles into the liquid, my breath was mixing with our water to create something called carbonic acid. And that's when carbon dioxide, the gas that we breathe out, mixes with water, and it actually creates an acid. And our indicator picked up on that, and you can see that it changed color and indicated. So that's one really, really interesting chemical that you can explore, indicators. And like I said, a lot of indicators in our household. And now we are moving on to our final demonstration. And our final demonstration is a chemistry demonstration, and it is one of my favorite chemistry demonstrations because we are going to be using some common household chemicals, but these common household chemicals are usually at a lower concentration than what we use in our lab. So we're going to be using hydrogen peroxide. And hydrogen peroxide, you may have heard of it, you may have not, is a chemical that a lot of times people use to maybe disinfect wounds, clean surfaces, but household hydrogen peroxide is usually about 3%. And the hydrogen peroxide that I'm using here is about 30%. So I'm wearing these gloves to make sure that they don't burn my skin, that it doesn't burn my skin. But the cool thing about hydrogen peroxide is that hydrogen peroxide can react with just the air around us, and it reacts with itself. So right now our hydrogen peroxide is undergoing a chemical reaction. But it's a little hard to see. And a lot of times scientists like to use certain clues to find out if a chemical reaction is happening or not. And one of those clues, or there are three major clues that we are going to be looking for when we look at our reaction. And those clues are a color change, maybe a temperature change, which might be hard to tell over video, but I'll let you know if I feel anything, and some new stuff being made. And right now, if we look at our reaction, I don't know if we're seeing any of those clues. So what we're going to do is we're going to help this chemical reaction along. And to do that, I need to get a very special piece of equipment. I need to get a little bit of dish soap. And this dish soap is going to help me create a more visible chemical reaction, or it's going to allow me to see the chemical reaction that's happening. So I'm going to drop a few globs of dish soap in here, mix it up a little. And, you know, we see our substance maybe look like it was mixed with dish soap, but I'm not seeing too many clues of a chemical reaction. So we are going to add one last thing, and that is some potassium iodide, which is known as a catalyst. And what catalysts do is they often speed up chemical reactions, make them a little bigger so they're a little more visible. So what I want everyone at home to do is I want you to look out for those three clues to a chemical reaction that might be happening. We want to look at a color change, a temperature change, and some new stuff being made. All right, are we all ready? In 3, 2, 1. Whoa! Look at that. I am definitely seeing some new stuff being made. I'm also seeing a little bit of steam coming off the top. That might be a temperature change, but you know, if you ask me, that was definitely a chemical reaction. And you know what? That brings us to the end of our show today. I hope you found some cool science demonstrations to learn from, and I also hope you found some things that you might be able to do at home. The science paper blow and the blow with the milk bottle or any sort of empty bottle or cup you might have at home are really, really cool things to try at home. And I encourage you to go to scienceworld.ca/resources for tons more really, really cool science activities that you can do at home. Thank you so much, City of New Westminster, and I hope you have a great family day. Hi everyone, this is Cindy from Science World, and today we are going to be talking about perception. So what you need for this activity is a bowl of warm water, a bowl of cold water, and a bowl of room temperature water. So what I'm going to do is I'm going to put each hand into a bowl of water. I'm just going to leave them in there for a little while, because what's happening here is that when we expose our bodies to a certain temperature, we have these thermoreceptors that will actually send that signal up to our brain that something is warm or something is cold. However, if we leave our hand in, say, a bowl of cold water for a really long time, those thermoreceptors will actually desensitize, which means that our body just kind of gets used to that temperature. Now, I'm gonna leave my hands in here for a little while. Usually I do it for about a minute or two. And then what I'm gonna do is I'm going to take each hand, I'm gonna put them both in a bowl of room temperature water. Now you may notice something really, really funky happening when you do this, and I would encourage you to try it out at home and share your results with us using the hashtag #ShowUsYourScience. All right, have a great day, everyone.